All right. So thank you everybody for being patient. Can you hear me now? Am I connected? I'm seeing
Yes.
people.
Yes.
All right. Ian has kindly offered to give us a presentation this morning. It's July the 13th of 2025, and Ian is going to talk on longitudinal electromagnetic waves, which is kind of a controversial topic. Okay, I guess we're ready to go.
Do you want to start immediately and load my slides or
Let's
okay.
go ahead and start.
Okay. So I've forgotten how to do this now. I have
Down
to
at the bottom green box.
share and you have to approve it. Yeah. Okay. Send request.
I just said allow. We should be able
Allow.
to go now.
So if I put up my slides, I may have to press share again. Can
You
you see
click
that?
on you click on. Did it give you the menu to select your slides from yet?
Um, I don't see anything different, no. Share is still in green at the bottom of the screen.
All right, now you need to click on your file for your where your slides are.
Right, I've done that.
All right, click share again.
Uh,
Bob, we went through this last week. Do you have any advice for him?
yeah, I remember Bob having.
No, I just try clicking on it. Make sure it's open.
There we go.
Oh, okay. Yeah, I had to open it and click share again. I think that's what Bob did last week.
Yeah.
And possibly, if I can get rid of these banners just upsetting my screen, I can maximize that. Ah, didn't seem to work. Uh, maybe that's it there.
There we go.
Yeah. Okay. Um, okay. I've moved this a bit away from the. Okay. Oh, okay. Well, thanks very much,
I'm
Harry.
sorry about the delay in starting. I don't know what happened.
I was just about to send you an email saying, "Is this going ahead today?" But you came on then, so
I I may have messed up. It didn't load correctly, and so I tried to cancel it, and then I started it again. It didn't load correctly, and I don't understand what happened. Whether it was just slow or it got confused, or anyway.
anyway, it did work at the end. So what I've done is I have prepared a few slides from some work I've been engaged in on, and having discussed it with Harry. We entitled the short presentation "Longitudinal Electrodynamic versus Transverse Electromagnetic Radiation." So I'll explain why I use the term electrodynamic in the longitudinal case rather than electromagnetic, which we always use in the transverse case. And I've actually been working for about 5 years. I was just looking it up, actually. It's about 2020 we started this with Dennis Allen. And he referred me to the work of J.P. Wesley, the late J.P. Wesley. So I thought I'd just acknowledge that. Now, I want to advance this, and it's not working for some odd reason. It's my own problem. And the photographs of us.
Try the arrow key.
Yeah, exactly what I'm doing, Jim. Arrow down, arrow to the right. Uh, I wonder if they page down. That'd be no use. No, it doesn't seem to have enabled my.
I think you need to go back um, to the left side and where, yeah, you don't have the different pages on the left side.
Yeah, because I've gone into slide mode, which
Or
perhaps.
maybe you get out of slide
Okay.
show and you can click on the ones on the left end if you're out of slideshow. That's
Yeah, I
among
pressed
them.
escape and I don't seem to be able to get out of the slide show. Uh, Let me see now.
Well, it doesn't
Escape
slideshow.
key. Try the escape key.
Yeah, I tried it and it didn't work. But I've got rid of everything now, I think. You can't see it, can you?
I see the first slide.
Yeah. So suppose I have it in this mode, share. Let's see what happens now. Oh, it's not coming up. That's very odd. You are screen sharing. Okay, maybe I didn't.
Here
There
we
you
go.
go.
Ah, okay.
Yeah.
Okay. I don't know. I think I clicked on the one with
So
the
we're back to the beginning now.
yeah, okay, we're back to the beginning. And I think I have control of the keys, but I don't have the thumbnails, which actually I'm glad about because I think they can be a bit distracting. So so um okay, just a summary of this whole concept. Uh, Normal electromagnetic radiation used in detection and ranging, or indeed generally in transmission and reception, that's what we refer to as Hertzian waves, is transverse. So the electric and magnetic field intensities and the Poynting vector, which is the vector cross product of E and H, are mutually perpendicular. That's generally accepted. Now, the general solution to the inhomogeneous wave equations, what we mean by that is where the D'Alembert doesn't vanish. If they vanish, you get a homogeneous wave equation equals zero. In this case, inhomogeneous wave equations admits also of longitudinal electrodynamic waves. And in this case, E and S are actually in the same direction, and H doesn't enter into it because you don't have any magnetic component. So this is rather revolutionary. Okay, now longitudinal waves are actually determined by the scalar potential. We'll be talking about scalar versus vector potential in the next slide. But so the ordinary scalar potential, electrostatic potential, which means that they are sometimes referred to, and I've done so myself, as scalar waves. Although, just a caution, this is not to be confused with Tesla's grand hugging waves, which, his famous experiments, I don't know, in the 30s or something, 2030. And they are sometimes referred to as scalar waves as well. So there's a distinction there. Okay, just before we get into the meat of the presentation, I just have maybe four publications. First of all, Wesley's book itself. So this is J.P. Wesley. I think most of you are probably familiar with him. He was an American who emigrated to Germany where he died. I don't think he was expelled from the place like maybe our friend. What's the friend? Sorry, I've just forgotten his name. The guy with the Redshift guy. No, just forgotten his name. Sorry. So Wesley wrote this book, Scientific Physics. Benjamin Wesley, Bloomberg, Germany, 2002. It seems to be most readily available from his widow, actually. So that's where both Denny and I got the publication. We just paid her a small amount, and she posted it to us. So if anybody wanted this, they could maybe let me know, and I could show them the ropes. There's another publication he excuse me, he subsequently made with God, all these names are escaping me today. Marquardt, yeah, Peter Marquardt, which is basically, I'd say, about three-quarters of that publication about photons and versus electrons and so on. I think electron mass. It's basically mostly the same as the scientific physics books. I have a copy of that second book. I was given a complimentary copy by Marquardt because Denny and I are actually are in communications with Marquardt about this whole area, and he actually is quite an interesting man. Although I think he would be the first to admit that most of this work is Wesley's, but he's been rather ill recently, so we've written him a few letters, and he hasn't replied. So anyway, but here is the classic paper by Christian Monstein and J.P. Wesley. So a joint paper where they set up a practical rig to try and observe these waves. It's called Observation of Scalar Longitudinal Electrodynamic Waves in this publication, EPL. he did the work. Monstein is Swiss. They did the work in Switzerland. So I'll be coming to that in a moment. I've actually added one more. So E.J. Butterworth et alia replicated Monstein and Wesley's experiments, longitudinal electromagnetic waves, but there's an interrogation mark there. So we'll come back to that. So the interpretation of Butterworth et al. Is actually worth looking at. The Monstein-Wesley experiment reconstructed, Journal of Scientific Exploration, and that was done in 2013, which is 11 years after the original experiments. And I just gave one more because this has been referred to me by Jenny actually. Bill Lucas Jr. He wrote one of these things in the magazine, I think, which he's responsible for, Common Sense Science. What is the nature and cause of life? Foundations of Science, etc., 2005. And in this, as far as I can see, he's giving some reasonably good reasons why longitudinal radiation seems to be associated with life, with animal or vegetable life. Like he's done, experiments where he refers to some earlier experiments on, even plants, which when they're living seem to exude a type of radiation which has the characteristics of longitudinal radiation, and then maybe when it's dead, it ceases. So just for information, I think that might be worth looking at. Okay, so just a couple of theoretical equations to remind you of the business. I think you can probably see my pointer. So we have the vector potential A at a position R, vector radius there, and at any time t is equal to this. J, where you have the dummy independent variable R dash, you're integrating over that 3 times integration, triple integration. J is the current density at the points there, and that's the difference between that. And the phi, which would be the scalar potential, similar, the usual notation is where rho is the charge density. Again, triple integration. Now, by the way, I call them my equations. I've just written them out in my particular idiosyncratic form. They're the same as Wesley's. Just in case you look at them, he's using Gaussian units, whereas I use SI. So just a caution on that. Okay. Now.
So to clarify, on the box down there where it says del squared phi 1/c squared, that's Gaussian units.
The next box. No, actually. Well, yes and no. I mean, if you look at Wesley's equations, I don't have them in front of me. I was going to bring the book away from my shelves, but they're there. I can get them in history. I think he would certainly have, del squared phi minus 1/c squared. But he'd have 4 pi. He'd probably have 4 pi rho.
All right,
Now,
right.
he probably should have 4 pi k rho, where k is the dielectric constant. But I think he might be introducing epsilon.
Okay, so those equations are in SI units?
My equations are all in SI units, yes. So, for example,
these are your equations with the 1/c squared factor in them?
yes. But I mean, they're standard. If you go to most of the textbooks, the one I think you use a lot over there, Jackson, he probably has the same.
I find it very confusing because everybody has different units, depending upon, they've recently tried to standardize on SI units, but Jackson sort of, resisted doing that. Anyway,
yeah.
go on.
Corson and Lorraine is the book I have, and it does use it. Now, I'm open to this. I use SI for various reasons, and I think there's a great, sort of consistency with them, and they also lead towards practical demonstration and so on. But on the other hand, I remember when I first studied first-year physics in college, they used Gaussian units, and I think the lecturers were making reference to what they were doing in the United States. It was one of the Ivy League colleges, and they said, "Oh, they're doing Gaussian units in first year physics, and therefore we're using Gaussian units for you," because it seemed to be a bit more heuristic. But I think there are contradictions, and I would actually advocate SI, I suppose. So B, the magnetic induction would be the curl of A. And E, the electric field intensity, would be the negative of the gradient of the scalar potential plus the partial time rate of change of the vector potential. And if you use the Lorentz gauge, or maybe all this gauge business, it's Lorentz condition, I might call it. Lorentz gauge or Lorentz condition, which is the divergence of A, here we are, plus, well, that's 1 over c squared, or you could put it
Yeah,
into
I
epsilon naught.
want to mention that it's not Lorentz with a T, it's
Yeah.
Lorentz without the T.
Yeah, perfect comment to make, Harry. Very, very good. I omitted to mention that, but it's worth mentioning. And in serious textbooks, dare I badmouth them? Corson and Lorraine, very academic people, they made a fundamental mistake, and they've Lorentz with the T. Uh, you know, actually, I'm always impressed. People who really know their subject have this because this is after the Danish physicist Lorentz. He was contemporaneous with Lorentz with the T, who was a Dutch physicist, Henry
Right.
Cantoon Lorentz, who's involved with the Lorentz transformations. There's another gentleman altogether. So, and I'll tell you, actually, it was another one. Denny brought this to my attention. It was. Believe it or not, Harry, you might laugh again. Jackson, he showed me that edition 1 and edition 2, Jackson made this cardinal error, but in additional 3 of his classical work, he had it corrected. So obviously somebody brought it to his attention. So okay, so Lorentz there. Well, basically, it looks as if you've taken this out of the sky, but it's really just a consequence of the conservation of charge. This Lorentz gauge or Lorentz condition. And it could be also looked at as if you take the quad operator, you know, the 4-dimensional, instead of taking the 3-dimensional nabla, the quad, the divergence of that of A vanishes. Or you can look at this, the div A plus epsilon naught mu naught, partial differential of the scalar potential with respect to equals 0. So it's the conservation of charge
And
equation.
you
Now, if you do that, just, so I say again?
The 1 over c squared has become E0 mu 0.
Yeah, some people mention that to me, and it's a good point. And I'm a bit inconsistent. When I put it out in the wave equation, I certainly put the 1 over c squared, but I've actually kept it in that form twice. And I accept your point. It can be a bit confusing to look at in this type of conservation charge. And also, I have another equation later. What is it? It's the induction, like the generalized Faraday induction law. I have actually kept the epsilon naught mu naught instead of 1 over c squared. But anyway, as long as you do, and others keep in mind that it's the same thing, you should have no problem. Okay. So anyway, if you play around with a bit of calculus and algebra and so on, you get the, as I say, the inhomogeneous doesn't vanish there. The wave equation there, D'Alembert, is minus the rho over epsilon naught. And this is where the 4 pi's would come in if you were dealing with Gaussian units. And similarly, you get the A vector potential, same thing. And this time you have the magnetic business. You know, it's a permeability, and you have the current density.
As
What's
I
that?
understand it, the homogeneous wave equation would be 0 rather
Correct.
than. So the homogeneous wave equation would be del squared phi equals 0 and del squared A equals 0 rather
No,
than.
not quite. It would be quad squared phi equals 0 and quad squared A equals 0. So in other words, del squared phi minus 1 over c squared.
All right. Okay. Gotcha.
You
All right.
follow that? Yeah. Equals 0. Yeah. So you need the time business in there.
It took me a long time to understand the difference between inhomogeneous and homogeneous. Believe me, it confuses me.
Yes. Yeah, that's fair enough. I played around with these for a long time, and you know, it's always good to discuss it. That's why I'm delighted to be able to recap on this with you, gentlemen, today, because you're obviously going to bring a lot of points in, and you've already raised about 3 points, which are actually very valuable, Harry. So thank you for that. I was fiddling around with these equations, and I must confess, on one or two occasions, I just lost patience with the maths, you know.
Yeah.
But anyway, you just persevere. Now, the solution of the vector potential wave equation, in other words, the second inhomogeneous wave equation, the one in A there. My cursor's coming on and off, so I don't. There it is. Subject to conservation one more condition from the Lorentz condition. Conservation of power density. So the power density is div S, the divergence of the Poynting vector. That's the power density. You know, it would be like kilowatts per cubic meter or something like that. And also the rate of change of energy density, which is D. So the rate of change of that. So if you impose that condition, conservation of that, this is where the mathematics becomes a bit tedious. It gives you the transverse electromagnetic waves. I think these are probably in the textbooks. I mean, I'm not diverging too much yet because I'm still talking about transverse. And S, well, you can see that actually if you look at it now in another form. That's E. S is equal to E cross H. You see that? Because that's E and that's B over mu naught, which is H. So it's a common, yeah, that's the Poynting vector. It's the common, it's Poynting's theorem really. But actually, Wesley would say that it's only a special case. The general case we're dealing with now. So Poynting's theorem, S is equal to E cross H, is a special case for transverse waves. And if you do the same in D, the energy density, actually this is where I differ from him. He put in E there. I know it's in italics rather than E bold, but I didn't like confusing it, so I've changed that to D, energy density. But you see, again, this is a well-known expression. I'm sure you know this, Harry. It's a half E squared epsilon naught plus a half uh, uh, H squared mu naught. That's the common expression for the energy density. So anyway, this is just expressed in the more fundamental terms of the potentials, phi and A. Okay. So that's well known, even though it looks a bit tedious, it's well known. And you get the things here. And this, you know, we've had discussions about this, but the E and the B are in phase and they're at right angles, and the S is working this way. And C, it's going at a speed C there. So that yeah, but that's that. Now, so we've done all that, and I've told you it's a bit of tedious mathematics, but those are the results, and they're the same as what's his name, Wesley's. They look different because of the different units, as you've acceded to, but they are the same if you look at them. Now, but what happens if we solve the scalar potential wave equation? In other words, the first homogeneous wave equation with similar restriction on energy conservation. Okay, there's no Lorentz condition now. There's no magnetic component, but we have the similar restriction on the divergence of the S and the rate of change of the D and so on. And I think I might have said this before, that everything which is not forbidden is compulsory, according to Murray Gell-Mann. I attended a talk by him about 20 years ago here in Trinity College, Dublin. So anyway, he's deceased now. If you do this, and you say it's verboten, you shall not do this because the mainstream don't do this. But anyway, if you did this, this would give a longitudinal electric waves with Poynting vector S and energy density D. So if you did this and you work through the maths in exactly the same way, you get there. You see, there's no A in this. It's merely based on the scalar potential. Okay, and that's what you get if you work through the maths, just from that second inhomogeneous equation. Just reminding you it's a longitudinal thing and compression, rarefaction, wavelength, blah, blah, blah. So we've done it. We've now broken the 11th commandment, thou shalt not do something which the mainstream would not do. And if you add the two, because you can add the energy densities and so on, you can add the power density. Well, you can that's the general equation for the Poynting vector and the general equation for the energy density. And I've just separated them into red transverse and green longitudinal. So you know, if you scrap the green, you get the conventional view, which, according to Wesley and me, I concur with him, is a special case of the general case. The Poynting theorem is a special case. So just bear that in mind. Now, okay, get to the paper where they try to produce this. So there's one thing to work it out theoretically. Not only is it not forbidden, but it seems almost compulsory. It follows from one equation. So what they did in 2002 is they they based a transmission and receiving apparatus on a ball, a spherical ball antenna. This is actually, unfortunately, I've used this R, where it's really the effective diameter plus a bit of the takeaway here, 79 millimeters. So it's a very small thing. It's an aluminium ball in their case, and all dimensions are given in millimeters. Yeah, I've taken this from their paper. So it's sort of a simplistic way would be looking at it would be the following. Transverse radiation is not produced by a spherical ball antenna because of complete symmetry. And sometimes this is referred to as the hairy ball theorem, where you would actually need a parting. If you think of a scalp of hair, and if you don't have a parting, it's all symmetrical. But if you part your hair with a comb, you'd have a discontinuity. But you don't have that. So that's what they say. This is going to produce. Well, I was going to say merely longitudinal radiation. I think they probably said that, but Denny and I have been saying, well, there may be a transverse component, and that may help to explain some of the problems that Butterworth et al. Had. We'll come to that in a moment. But anyway, so the more theoretical way of expressing this would be, and I'm quoting directly from Monson and Wesley's paper, they say the spherically symmetric current density J within the ball that gives rise to the pulsating surface charge is divergenceless. Div J equals zero, so div A equals zero, and furthermore, curl A equals zero, and no transverse wave can arise. So they say they were detecting only longitudinal waves. I'll give you the evidence for that in a second. But I think I might say I'm not clear of that. It's probably largely longitudinal, but there's probably a transverse component. Anyway, we come to that. So I perhaps have just 3 slides on the practical paper, which I've given the reference to. Producing longitudinal radiation by Weinstein and Wesley, and this is 23 years ago. So they had this. We've talked about this before. I think I mentioned this before in a further paper. A rotatable cubic array polarizer analyzer with half wavelength rods. So these are lambda over 2 in length. And it's rotatable either by hand or by an old-fashioned turntable. They had that. And so here's the normalized power transmission. They're using the decibel ratios there, but and the flexion angle. So when the rods, the lambda over 2 rods, made of brass, are transverse. So when they're in line, let me say longitudinal waves that's the frequency they use, 334 megahertz, passing through the polarizer as a function of polarizer, and the angle between the direction of the wires and the direction of propagation. So in other words, when the propagation was in the same direction as the rods there, you get 0 power transmitted. But when they're at right angles, here, plus or minus 90 degrees, you get maximum. This is normalized, actually. So they're saying that, this acts as an obstructor to the longitudinal waves because they're moving longitudinal. It wouldn't act as an obstructor there to a transverse wave. But there is some spread there, so maybe my theory that they are getting some transverse components is not totally wrong. But this is interesting. This is the last one on their experiment. I'm really summarizing it very quickly, and those of you who really want to go into it will discuss it in the sessions, and I'll refer you to the paper and all that. But So they did this in a place called Sennwald in Switzerland, which is on the banks of the Rhine River. Transmitter and receiver, the height and all that sort of thing. Here are the bulls. They're identical bulls, actually, X apart. Ultra high frequency transmitter left, portable receiving system right. Both installed on the bank of the River Rhine. They're spelling it there in sort of the German way. The received power here is in dBs as a function of distance x, where x was measured by a GPS system. The dots show one V1 of one of six experiments. The solid line shows the values given in equation 14. He's worked out an equation which I haven't given you. I think he might have referred to it back here actually. This is the type of equation. There's a factor in there, K, and he got the value of 4.4 just by fitting best fit, least squares fit. But the thing is, here, the results are the dots here, and this is his theoretical business here. Now, there are two interesting things that I wish to point out here, gentlemen. One is that this decay with increasing distance seems to be a greater decay than an inverse square decay. In fact, what it actually appears to be is an exponential decay imposed upon an inverse square decay. And that has been postulated to be due to an induction in the plane of the Earth, ohmic losses due to an induction in the plane of the Earth. Now, if that is so, it would certainly fit in with this business. You'd have an exponential decay. But if that is so, Monson and Wesley say, well, that's another proof that we're getting longitudinal waves because with transverse, they're in the direction. The ohmic losses and the induction in the Earth is in the direction of the transmission of these longitudinal waves, the way the energy is going. If it had been transverse, you would have been at right angles to the plane of the Earth, and you wouldn't get any induction. So that's the power level. Now, actually, I don't know. This mightn't have been worth the candle, but we were trying, Denny and I, to get an experiment. A further experiment on this. And I did say to Denny, look, it's been done already by these guys. Now, these gentlemen, Butterworth et al., came to a different conclusion from the one I'm advocating, and that's my next slide. But nevertheless, they did get their same results as Monson and Wesley, so that's quite impressive. But we were in touch with some people, and I think I gave a paper on this some time ago about the idea these autonomous vehicles and so on. And one of Denny's sons works in the Department of Transport in one of the states. I've forgotten which state. And they were looking at this, and we were sort of liaising with him about maybe having autonomous vehicles controlled by longitudinal radiation. Because the fear actually is Minnesota or somewhere like that, I think it was. They said they put these systems up, these transverse radiation receivers and transmitters on the median of the highway. And then in another 20 years, don't you know, you're going to have a raft of legal action against Minnesota Department of Transport by all these drivers claiming that they got cancer from this or something. But, as people like Lucas point out, this radiation is fairly innocuous. Anyway, but that's water under the bridge. So there was a gentleman by the name of Walter, quite an interesting gentleman, who's done a lot of experimental work, and he's also got a PhD. He's quite theoretical, but he's forgotten all his equations. When you put these equations up, he said, "You've lost me." But I think again, he's a rather elderly gentleman, and he became quite ill. He's probably 90 by now or something, so I don't think we're going to get him to. He has laboratory facilities, which neither Denny nor I have, because we're retired, and I told them I had metrological facilities years ago. I don't have anything now. Anyway, so just if you did do this and you take the general integration, and here I've kept that would be 1 over c squared, as you point out there. So the general business there. And again, frequently they I've talked about this in my Hertzian analysis of transverse electromagnetic radiation, where you have a total derivative. So Here we keep in the terms. Do you remember that? I've just got the.
All right.
I've
We
expanded
got
it.
4 minutes.
Okay, I'll hurry up because I didn't know if you wanted me to go into the next session. So I got by triple integration you get the inductance is proportional to the radius. We made approximations for the capacitance, the inductance, and resonant dimensions and all that, and the resistance. And for Monson and Wesley's, we got the frequency 434 megahertz, the distance, which is really the diameter of the ball, 79 millimeters. The capacitance is 8.4 picofarads. L is 0.01 for microfarads, and the resistance is 0.167 ohms. And the signal is to be fed to the core of the coaxial cable in the transmitter, and the sheath is earthed. Now this is the last slide actually, so I hope I'll finish it before we have to go into the next one. I say the theory has demonstrated how longitudinal scalar electromagnetic radiation may be produced. This has been demonstrated experimentally by Monstein and Wesley and reproduced by Butterworth et al. Of Texas A&M University, Kingsville. Though, having done all the experiments, Butterworth et al. Say, well, they counter the theory and the very existence, indeed, of longitudinal electromagnetic waves. And I'm quoting there. They say, at the end of their paper, they got the same results effectively as Monson and Wesley. They say, we dispute MW's claim on theoretical grounds. We conclude that a yet unidentified mechanism must be producing the observed results. Dear, oh dear, all I can do is finish this short presentation by quoting the words of Samuel Beckett. No matter, try again, fail better. Thanks, gentlemen, for your attention.
All right. Well, we got 2 minutes. That's very interesting. I've seen a lot of this before. I've read both of the papers. Yeah, it's kind of the when we come back, I think might be worthwhile for you to discuss what the that polarizer thing that I'm not sure what that polarizer did. I think it was placed in front of the antenna to eliminate the transverse waves. I'm not really sure about that. So you might want to talk about that a little further. Okay, does anybody else have any comments here? We got like a minute and a half. No questions, no comments.
Well, I'm interested in the duration of the signal because how is this like a pulse, a very brief pulse, or what?
I think it's a CW, continuously transmitted signal.
Yes. I mean, it said something
Oh,
about
wouldn't you then have
generation.
a continuous reception?
It is, yeah. I think you probably
Well,
got the
how
idea
is a
somewhere.
longitudinal wave even detected then?
Sorry, say that again.
How is a longitudinal wave detected if the signal and the reception are continuous?
Well, you when we say continuous, you have a continuous wave, and you observe that. So in other words, you're getting a signal from your ball receiver, and that's fed back to some sort of analyzer. He had quite sophisticated equipment, by the way, and even brought he had it all brought down to the banks of the river there.
I think the filter is to filter out the transverse wave.
Yeah, that's what the analyzer polarizer did, and one might. Well, I'm saying I've.
Okay, well, welcome back. Excuse me. All right. I think part of the issue here has to do with understanding how the setup of the experiment is done. That's what Jim's question, I think, is directed at.
What really? Okay, we have all the equations that you presented, which are to some extent based upon the theoretical understandings, right? to me, to really understand and to dig into it, I need the operational definitions. I need, okay, we have a counter here, and when it reaches a certain count, bingo, we say that is equivalent to the existence of a longitudinal wave. In other words, what are the operational definitions in these experiments?
Well, apparently that's in dispute because of the second group did the experiment and disagreed. So,
yeah, well, that's one reason why I'm focusing on it. And the other reason is just so I can understand what the hell is going on.
well, they did an experiment, and apparently there are two different interpretations of the experiment.
Well, from what I can gather from Ian's presentation so far, is that they're saying that if we get a signal and we have filtered out what we think are transverse waves, then the presence of a remaining signal, a residual signal without transverse waves, that is equivalent to a longitudinal wave. Is that really a fair statement?
According to the first definition, in other words, the first experiment, but the second set of experiments by Butterworth, they say, yes, you're getting something and we've filtered out transverse, but God knows what's happening. We're getting something, we don't know what the hell it is. It's not longitudinal because longitudinal radiation cannot exist by orthodox theory. That's a summary of what they're saying, as far as I can see.
Well, that's why I'm really asking how longitudinal is actually defined, especially when you have a continuous signal. Wouldn't you want to have some sort of a pulsed signal, a brief pulse, and showing that pulse generates an event or a series of events which is of greater duration than the original signal pulse length, and therefore we could say, aha, there must be something longitudinal going on here. In other words, I think it all comes down to the operational definitions of what we're actually talking about.
I don't see any fundamental difference between this and transverse radiation. I mean, what we're doing is we're generating by various oscillatory systems Hertzian waves, and I suppose that's what Hertz did originally. Following Maxwell's ideas and so on, and then he got on the receiver. He got a corresponding signal, and when he stopped the signal in the transmitter, it stopped in the receiver. And then he started analyzing those waves. Well, I would say it's exactly the same, except in this case, you're getting a signal which is dependent upon the signal you're feeding into the transmitter, which is some sort of variable wave pattern. And when you stop one, you stop the other. But as we said, the analyzer polarizer shows that it is it's let through when perhaps it should be impeded if it's transverse, and contrary-wise, it's attenuated when perhaps it should be allowed through if it's transverse. So everything is on its head. So there must be something different. I mean, these Butterworth people concede that they say that it's an unknown phenomenon. They just cannot bring themselves to say it's a longitudinal wave. There's something there, Jim.
Okay, I think one of the things is that when you go back to that diagram that you showed, which was the results, that they make a prediction with their theory as to, they have a theoretical prediction and then they have measured results compared against it. That was done by Wesley and Monstein, I take it.
Correct.
And you don't show any of the results from the Butterworth, Texas group. But apparently they got something similar. And it might be interesting if you had that in your presentation.
Yeah, that's a good point. I'll have to look at that again because I sort of read through the paper and there may be some information there which I could easily have put up on a slide.
Yeah, I've read both papers, and I kind of am mystified as to what Wesley and Monstein did, and I'm mystified as to whether or not the Texas guys really did the same experiment or did something different because they misunderstood what, because it seemed, but the idea as I understand it is that because you have this spherical ball antenna, that antenna can only respond to longitudinal waves. That's my understanding of the thesis of the experiment. And you have two identical antennas, one as a transmitter and one as a receiver. And because they they can't generate transverse waves according to the theory says they can't generate or receive transverse waves, and apparently they do. So what Butterworth, I think, is saying that something's amiss here. We don't agree that they're longitudinal waves, so something must be amiss. I think that's what their conclusion is.
Yes, I think you're probably true. You're probably right. Although I think the original Monstein paper would not say that there's a small component of transverse waves. That's my expression, and I may have, whether you accept it or not, misled you a bit there. But they claim no, because as you say, a priori. Only longitudinal waves can be generated by this piece of apparatus because of the basic
Correct.
theorem there. And then they say they generated it by showing that this polarizer is in line with there being longitudinal waves. And then to boost, they have the thing doesn't go off as the square of the distance. But it falls that plus another factor which can be modeled as anomic loss due to induction in the Earth, which would only apply to longitudinal radiation. So that's what they say. Those 3 points are basically Monstein's point. Now the Texas guys, it's very good. I'll have to look at that a bit more to see how far they say they replicated it. They don't say no, we didn't get this or we did get this. They didn't say what I've said, as far as I can remember, that there's a component of transverse. They just said there's an unknown phenomenon here. There's something happening, and we'll have to look into it.
Well, is that equivalent to basically stating that the Maxwell's equations, which form the basis of a lot of this work here, are in fact incorrect or incomplete?
Yeah, I think it would say it was incomplete. There are people who have different biases, Like I note from the correspondence, and I'm not reading every single line, but people like David Tome, to him Maxwell is like a god, and he doesn't like to. And then other people say he's rubbish. Turn it out. So my own view is Maxwell's equations can be claimed to be in certain respects incomplete, but they're not incorrect. I think they are correct. The basis.
Well, I'm assuming that this particular claim of longitudinal is that the belief regarding Hertzian waves, that the Hertzian waves is not the only solution, that there's an additional solution called the longitudinal wave, as you're referring to. And so therefore there ought to be two types of waves emitted because the mathematics admits two types of solution. That's the thesis.
And I presume, as far as I can see, Harry, that comes out of Wesley because he did this theoretical work probably in the 1990s or something. I haven't seen it anywhere else. And that prompted Monstein and with Wesley, yeah, the original man, Wesley probably proposed it to Monstein because Monstein is quite an accomplished radio ham person, and he's also an astronomer. He has quite sophisticated equipment. I didn't mention this, but maybe I'll mention it now, although we are being recorded. Denny informed me that he got into a bit of trouble in Germany. I don't know what. He was doing some work, and he said the longitudinal waves, and he was threatened by a high court judge. This is what I'm just repeating what I hear, for that he could get into legal difficulties and he could be imprisoned in Germany for saying this.
Yeah, I've heard this story.
Did you hear that story? Wordsworth.
Now we're talking about Monstein now, who's a ham radio operator.
Yes.
Okay.
You've argued the similarity of light wave transmission and sound wave transmission, Ian. Would it be correct to say that sound wave transmission is basically a longitudinal wave, with compression and decompression, so forth.
Well, yes, yes, that's quite so, and I've used that analogy, and the equations would come out as well. I mean, you have people like Franklin who go, in my view, to an extreme. They say everything is longitudinal. That's the other extreme. They say there's no such thing as transverse radiation. But yes, Jim, that's the analogy I use. And by the way, just adding a bit about Monstein, sometimes you have some of these people who've done a lot of very extensive work, and I suppose the demand upon their time is quite significant. So you find they don't respond to requests. Whenever Denny or I have written to Monstein, he's come back to us with a couple of pages of his original. He gives us all the details about the original experiment, and so he's quite open. If any of us want to approach him again, he will write to us.
Okay, so he's still alive.
Yeah, well, he was alive when I contacted him last, about
Okay,
2 years
all right.
ago. He's not. He'd be younger than any of us here. Well, maybe with the exception of James. I don't know. He's not. He's probably a middle-aged man. I don't know.
All right.
Well, is it correct to say that the Butterworth, Texas people and the original work basically got the same results, but are interpreting them differently? And if so,
Yes.
what is the fundamental difference or deciding issue, if you will, in this dispute on result interpretation?
It's a good question, Jim, because there was one little
Well, thank
aspect,
you.
yeah, which you can delve a bit further down into it, which I didn't raise, and I have to remember it now. So what's the theoretical reason that Butterworth just reject this on theoretical grounds and so on? And what they said, do you remember I gave that equation about the divergence of J vanishing and so on? Well, and this is the case in free space, but they said, oh no, it cannot, because you have to bring in the charge density into that. So like div J would equal whatever it is minus d rho by dt or something. Um, and therefore you cannot take a divergence, and therefore you
Well,
cannot take
that is the question I have about the equations you presented. If for example, div phi or div a are equal to zero, why are they appearing in those equations?
well no,
So you just have a zero in there.
yeah, you get the general A, and you have the vector potential and so on. But for this particular case, so it's argued, and Butterworth reject this. For the particular case of a spherical ball, um, you have that the div J vanishes for the reasons they gave about this hairy ball business or parting and so on. And therefore, if you look at this big triple integral thing, well, the div J disappears, and therefore you get the equation. I can remember the equation. I have to put it up now. Uh, Anyway, the bottom line is that A is still a very real existing phenomenon. It's just that its divergence and its curl as well actually vanish in this particular case for this symmetrical ball.
Right.
But
So that's the
A still
basis
exists.
of the idea that it doesn't transmit transverse waves. The antenna is in theory incapable of transmitting transverse waves. The ball.
Yeah.
So
And
if we had an antenna to detect transverse waves, which apparently they didn't have, we would have detected none. In other words, the whole idea that this ball antenna, and I'm not an expert in this, so I'm just trying to keep things simple in my mind here. The idea of having this ball antenna and saying there are no transverse waves detected, I would think if you're setting up an experiment, one of the first things you would do is set up an antenna which is very good at detecting transverse waves, and be sure that none are being emitted by our ball transmitter antenna. Wouldn't that make sense?
Yeah, unfortunately, the problem is that's um, suppressing transverse waves. You know, you in theory the ball shouldn't transmit transverse waves, but you've got a transmission line and things that connect to the ball and other pieces of equipment that could be transmitting transverse waves. That's the problem.
Well, yeah, or even the ball might be less than perfect. So the
Right.
assumption well, I assume that the transmission lines are shielded, but at any rate, I would think that if you're going to trot out and say, I've got a signal generator which will not transmit or produce transverse waves, the first thing you would do would be to test for that. And apparently, no test for that has been presented.
Well, it's a different test. I mean, I think you're proposing, Jim, that if you had a receiver which was tuned and designed so that it only received transverse waves, you'd be able to resolve this problem. But what they did is maybe it's a bit primitive. They just put in this array of brass wires of lambda over two in length, and they were saying, well, that would block if in a certain orientation it would block transverse waves vis-a-vis longitudinal waves. So in a way, it did the same thing as you're proposing, I think, maybe in a more primitive way.
Well, but in the U-shaped graph that you showed, um, it is it not then demonstrating that this ball and antenna is producing transverse waves, which are blocked? So like the whole credibility of the thing comes into question. Again, I may be missing something, and to a certain extent, I'm sort of probing what am I missing in this, because it seems like this is not a very these people apparently are not good experimentalists, experimental physicists, because some of the basic tests that I think you would do in setting up this thing were are simply absent.
I mean, these comments are very valuable, and it's good that you haven't been intimately involved in this. It's always good to get an analysis. But my own view, for what it's worth, is that Wesley might not have been an excellent experimentalist. He's a theoretician. He's a very good theoretician. But from what I've seen, Monstein is an excellent experimentalist. And he's gone into all these details. And he's, well, I
And
mean,
so you're saying so, and so these great guys are saying that their ball transmitter is not producing transverse waves, but
yeah.
then they turn right around by rotating the screen that they have and saying, well, you see, we can block the transverse waves.
Well,
So
well,
which is it?
well, no, I think they would say that we've proved that they are transverse because this system will only operate in this way with the U curve for longitudinal radiation. It would be the converse, it would be like a peak or something for transverse. So it's a
So
U.
so why use the ball antenna in the first place? Why not just have two ordinary antennas and block
Then you
out
generate
transverse
transverse
waves?
waves.
Excuse me?
Then you would generate transverse waves. They didn't want to generate
Well,
transverse
apparently
waves.
they are generating transverse waves if the orientation of this blocking filter in between the transmitter and receptor.
No, I think that's wrong. And I may be partly responsible for putting you over a bit. They would say they're not producing and they're not blocking transverse waves. They're blocking longitudinal waves, and they're blocking it in such a way that when the thing is in line, you get a blockage, and that would only occur for transverse waves. I said just by the way, that I think that they may not have had zero transverse waves. They might have had 0.1% or something, and that might be the scatter and so on. So they would say no, they're only producing longitudinal waves, and they've proved that by having a piece of apparatus that would operate in this way with regard to blocking longitudinal waves, not transverse waves. Now, I don't know if that answers the question very well because I'm trying to interpret what they would say, And I might be not 100% behind them. I'm 99% behind them. But they're good points.
Well, in view of the unexplained phenomena claim,
Yeah.
I would think that different approaches would be utilized in this work.
I think that's what he said at the beginning, where he was talking about doing some experiments. Um,
Yeah. We have been working on trying to get experiments, and we were nearest with this guy Walter. Although I think Denny is actually in correspondence with people like oh, what's his name? The man who sometimes participates in our work. Eric Reiter at the moment, because he has some laboratory facilities. But I don't know why there has been so little interest in this. If this really is an unknown phenomenon which has surprised these Texas people, why haven't they some major project now to try to sort this out? Why were Monstein and Wesley the first to do this about 20 years ago? Why has the theory only come to the fore maybe in the last 30 years by Wesley? Well, maybe that's easier to explain because he was quite an original thinker, and he's he has a gravitation theory, and he has theories which contradict the special relativity and Lorentzian relativity and all that sort of thing. But it's very recent, and there haven't been repeat experiments on it. And I think, I mean, I was a bit dismissive in my last. I was a little ironic there when I quoted Beckett and so on. But um, I think if I were an academic now, making a proposal to a body, the government body or something that might refund some research into this. Uh, I think they would just say you're speaking through your hat. The orthodox science says this doesn't exist, so you're just wasting your time. And if they did a bit more research, they would say, well, these experts in Texas Kingsmill University have actually got these results. They've done it all, but they're experts. They tell me that it isn't longitudinal. It cannot be. So you're wasting your time.
okay, I want to interrupt you a little bit here. I know that James had a question. I did want to bring up um, Mr. Lucas. I know that um, he gave a number of presentations years ago. He's talked about this longitudinal wave thing quite a bit, and and we haven't really touched on him at all. And it's not real clear to me what his health situation is. We haven't heard from him in years. He used to show up quite regularly on Saturday mornings, and now I haven't heard from him in years. Um, so anyway, I did want to mention that he's done a lot of theoretical work on longitudinal electromagnetic waves, as you mentioned in your introduction. Okay, James, I guess we'll let you go with a question or comment.
So I've got a couple of comments on the experiment. It's obviously in air, isn't it? It's not in a vacuum. It's not, and it's about a meter length or of that order. The wavelength of the
A little less than a meter.
Yeah.
or is under a meter. So my question: when you've got high voltage power lines, you get this fanning effect on the insulators, and it helps cool them. So when electromagnetic waves go through air, you can get absorption and you can get heat transference, which would explain why they're going down faster than 1/r². If you're getting the radiation absorbed by the air molecules and then heating up and fanning. So was that considered? I mean,
and you could almost be
it's
talking about a plasma as well. It could be ionized. But no, I don't recall
yeah,
that.
that's an induction effect in neutral air molecules, but it's the same as in much lower frequency when you're having with high voltage pylons on the insulators.
Yeah, no, it's an interesting point, and I'm just going by my recollection because I just revised my study of this maybe some days ago in preparation for today. And I don't recall them going into other possibilities such as that, which might be very pertinent, James. I think the phraseology with regard to the induction in the plane of the Earth, it was they weren't saying, look, this may be so. They say we 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 would propose that this is probably the case, and it would explain. It would be if so, it would give another factor which would lend credence to the contention that these are longitudinal rather than transverse electromagnetic. So, in other words, they're not totally dogmatic and saying this is the only reason, and anything like what you might say is not the case. But you see how they cage their words a little. They say this is a preliminary explanation for this falling off.
Yeah. So you've got to eliminate the air effects. The other question is, you mentioned about life emitting longitudinal. There is a company in Aberystwyth who makes this sensor based on radio frequency. It basically senses how much yeast is in beer, and it basically live material, or the stuff that's living, has a thin layer, a capacitance layer, and you can detect live yeast from dead yeast. So there is a capacitance effect with life over death, which is it's utilized for a yeast detection in the beer industry with this company. So you've got to worry about these sort of things as well, and you can't just say life emits this certain radiation, but it does have different properties of capacitance effect. So you've got to eliminate the what's emitted and what's you're measuring by pointing your radiation at it.
And that fits in with the Bill Lucas business that Harry's referring to there. And as far as I recall, well, as we know, there might be a join up here because capacitance is a central factor in this whole business of longitudinal radiation. So remember, for the transverse, we have capacitance and inductance. But the magnetic thing is not a thing. By the way, there was one other thing I did omit to mention. Perhaps I just mentioned it now. As I say, capacitance is the central issue, and what you've just said about this yeast business could actually tie very much in with Bill Lucas. It's probably a pity we don't have him around. I hope he comes back soon. But you remember that when I was talking about the transverse case, with the magnetic vector potential, I obviously had a phi term in there as well. And when you expand it out, you get grad phi squared and so on. Now, there is a difference of opinion between me and Denny on this. Denny says that Wesley has double counted there. He shouldn't have the scalar potential in the transverse case. Well, I disagree with that. I said I worked it out and I got the same equations as Wesley. I think that it's correct to have the grad phi term in the, that term as well. So it's just a minor point. So Denny's equations wouldn't have a 2 phi squared there. He'd just have a single phi squared. But I have the full equation. E equals minus grad phi plus delta A by delta T. So just point that out to you. So two things are important from what you've just said, in my humble opinion. One is the capacitance effect, which might tie in very well with the experiments you've talked about the Aberystwyth there. And the other, the slight difference of opinion as to whether the phi should occur in the transverse case at all.
Yes. So you basically, if you were going to repeat the experiments, you'd want to do it in vacuo, at least as a control, to see whether the effect was repeatable in vacuo.
It would be, because they did it in open air and it was subject to a lot of perturbations and so on. It's open air laboratory. Yeah.
And molecules do absorb quite heavily in some of the radio frequencies, so you've got to watch what radio frequency you're using, just in case you're hitting an absorption band.
This is below that range. This is in the 300 megahertz range. You're talking about microwaves.
Yeah,
Mm.
It might be interesting to do it at different frequencies.
Well, they absorb it all through frequency, don't they? From light downwards, low frequencies.
434 megahertz.
Maybe it's a bit long it's because it's a
Yeah,
Okay.
that's like about a meter, a little
Yeah.
less, 3/4 of a meter, I think, wavelength. Okay, we
You
got
see,
4 minutes left, I think.
I think I've proposed to
No,
Denny
8 minutes.
that I should contact Monstein to ask him to give a Saturday presentation. You see, I've gone to very interesting people, high-powered people, and I think Denny said to me, "Don't." He couldn't give it because he'd be afraid of being imprisoned because of
Oh,
the. Sorry, so I took his word, but maybe you guys might be able to push me into contacting him again.
Sounds like he violated some radio rule in doing this experiment.
Okay, I was wondering what it might be. I don't know.
Well, from what I'm gathering, at 432 megahertz, that should have been legal. Might maybe in Germany. I know it would be in the United States. I'm not sure about Germany. Maybe they have some. Maybe they have some issue, some technical issue that, the Germans are real particular about obeying all the rules exactly.
Protecting the frequency and obeying all the rules. Yeah.
Okay.
That's a reasonable explanation. I was wondering what it might be.
I don't really know. It sounds peculiar, because usually, people don't pay much attention to ham radio operators, at least here in the United States. Maybe there's more regulation in Germany. Sounds like he stepped on somebody's toes.
Yeah, and I think he said to me most recently that he's now not doing work in this area. He's restricting himself to the astronomical work that he's involved in.
Right. Okay, we got 6 minutes.
Do the ball antennas have any directionality either in sending out a signal or receiving it?
Good question. Don't know.
Yeah.
I think Vladimir wanted to say something. Okay.
Yes, sir. I was waiting for my turn. First of all, I would like to support the question of Jim. As an experimentalist, he's absolutely right. I want to continue these questions about the details. If you want to confirm something very strictly, you must take care about all the experimental details. First of all, his experiment, very good one for the beginning. The second one, how spherical is receiver and emitter? How spherical? Who tested it? The next question, very important one. Blocks, all the blocks, they never have absolute effective, absolutely like ideal block. All of them, they have a contrast ratio, means how much you have in one polarization against another one, and so on and so on. That's why this theoretical work, mathematical work, as usually, without details, very thoroughly checked details about experiments, it's absolutely not not proving anything. But even in case, these longitudinal waves does exist. Okay, let me ask you the question: what is the advantage of these wavelengths? What we're going to use them? How they better than our standard transverse
Well,
waves?
the latter one
Let
I
me
can
ask you
answer
the question,
quickly.
because physics it's an experimental science. That's why if you have some experiments, show me where you want to apply these experiments results.
Okay. I mean, the first few points you made are interesting and they'd have to be looked into, and one would have to see whether they're just second order effects or whether they're, seriously doubting the results. But with regard to the last point you make, um, the contention, I think probably Bill Lucas referred to this as well, that these were benign waves. There's a controversy about non-ionizing radiation and its effect. We know that ionizing can be quite dangerous, but non-ionizing may or may not be. So people are concerned about microwaves, or they're concerned about phones, held to your ear for a long time and so on. And so, in other words, conventional transverse radiation, maybe in the higher frequencies, can have some long-term deleterious effects on the operation of the body and the cells therein. Whereas, and I think it's probably Bill Lucas is coming to this. He appears to have shown that these are totally beneficent. Well, if anything, they're not harmful. The longitudinal wave has no negative effect on cellular tissue, whereas we do know that actually transverse rays do. So that's one of the reasons. That's why this project that also was stillborn, unfortunately, this project about 2 or 3 years ago, to put up these ball transmitters and receivers to aid an initial experiment in, I think it was the state of Minnesota, for transport. Maybe not only autonomous vehicles, because that's a bit in the future, but maybe for connections to motor vehicles and communications and so on. We were looking at doing a pilot test. So I don't know if that answers your question, but that's what the advocates would say. I'm a bit of a theoretician. I have my head in the clouds, and I'd love to know whether, maybe a bit like you, but I'd love to know whether longitudinal radiation of this form, which seems to come out of the equations, does exist, irrespective of.
And what are we assuming that if longitudinal waves exist, that their velocity is the same as transverse waves?
Okay, that's a very good question. That's a very good question. And I've been looking at that myself, and I don't think we've come to a definitive answer on that. I think, you see, it depends what you mean by velocity and so on. But my own analysis of this, which is only preliminary because I haven't got into it, and we're not even in agreement whether these waves exist. So can we find out what the speed of transmission is? But I think what's coming out of the theory is that the speed is orders of magnitude. It might be 10 to the power of 8 times the speed of light or something. I don't think it's the speed of light. The speed of light comes out of the epsilon naught mu naught business, which is both. It's electromagnetic. It's not electrodynamic. Electrodynamic, you just have the phi and the epsilon naught, the capacitance and the scalar potential. So I think it's rather like the establishment of an electrostatic field, which is not bounded by the speed of light. It's almost instantaneous. But work would have to be done on that. You're right. This is a very fruitful.
What evidence for instantaneous electromagnetic field is there?
Okay, okay. So you're coming back to the evidence and experimental, and quite rightly so. Yeah. Well,
we could just talk about pretty ideas all day, but
we're going to get stopped here. We got less than a minute. Do you want to continue on with this later?
Do you want to continue with the conversation? I'd like to deal with the point you just made, even briefly. We might be able to come back to it, but
yeah, I doubt you're going to get it in. We're less than a minute.
Okay. Well, wait till we come back in the third one, shall we?
All right. Okay.
Thanks, Ian.
Thanks, Jim. I must say it's very stimulating what you're saying, and we need you guys to feed in.
I've got more questions. I've got more questions.
Good. The more the better, and the more they tax one, the more welcome they are.
And Vlad's questions were also very appropriate.
Questions.
Yeah.
All right. It should cut off here pretty soon.
Okay.
Okay. All right. So do you want to, I think we're back.
And it's Jim here. He is, yeah. He's got a static photograph there.
Recording is going, so.
Like he was asking about the evidence for the speed and all that, and I am speculating, I must confess. But I might go back to Wesley's work because he actually has a chapter, I think it's chapter 3 in the book, which shows the same equations for the gravitational field as for the electrodynamic field. So we're talking about electromagnetism plus electric fields. And well, the equations would seem not to restrict the speed of transmission of the signal. So, and we know, well, I claim it, and I think many people agree with me, Jim, that for gravitational interaction, say Tom van Flandern has shown that he gave about, oh, I don't know, about 7 experiments. For example, during a total solar eclipse, the maximum time of interaction, gravitational interaction between, say, the sun, moon, and Earth when they're in line, is not the same as the time of maximum eclipse. And then, of course, there's this business about the
So
non-apparent.
you're talking about the velocity issue now.
Yeah, because that's what Jim asked, didn't he? He said,
And it's related
why
to
did I say
action
that it
at a
might be the speed
distance,
of light?
magical action at a distance.
Yeah, quite so. So magical action at distance, I prefer to say it's not infinite, that, in a distant part of the universe, you don't have an infinite thing, but it might be such that would make, light years transmission occur in fractions of a second, because it might be 10 to the power of 12 times the speed of light or something like that. And this goes back to people like Laplace, and people like that, going back hundreds of years, where he did some theoretical calculations based on Newtonian theory and Lagrangian dynamics and so on. And he estimated that in view of the known stability of the orbits of the planets, which have been detected over long periods of time, hundreds of years, the speed of light would have to be at least, I think he said, the speed of gravity, sorry, would have to be at least 10 to the power of 8 times the speed of light. He was probably saying this about 1800 or something,
I wonder how he pulled that out of the hat.
Well, you can work out that suppose the speed of gravity were the speed of light. Well, then you can work out the period of time over which the orbits of the planets would spiral out. So he did all this by plugging the values into the equation. So in other words, over maybe, I don't know what it might be. If it were the speed of light, actually, probably in 50 years, the Earth would just fly off to infinity and be lost from the sun. So he says, look, we know the planets have been stable for hundreds and hundreds of years. So the speed of, if the speed of gravity were 10 times the speed of light, over maybe 200 years, the planets would spiral out, because you would have an effective couple owing to the aberration caused by gravity. You would find that gravity would be like light, that the instantaneous position would lag, say, between the sun and the Earth, for example, by 8.3 minutes. And therefore you would have a couple. It wouldn't be, just a straight line interaction. You'd have a couple acting on this, and this would lead to the Earth spiraling out. So he did that. Now Van Flandern has updated that, because he's given, another half dozen or more experiments that have been done with pendulums and all that sort of thing. So now on the electrostatic side, I think there's something similar. There is some information, and I'd love projects to be done to accelerate that. If you establish an electrostatic field through a capacitance bank or something like that, when is the effect felt? Now, the theory of relativity would say, well, it would take a small amount of time, because it has to be transmitted by the speed of light, c. But it seems to be that things like electrostatic fields are almost instantaneously established. The effect can be seen. So what I do is we don't have enough data. I agree. You're asking these correct questions. I'm a bit of a theoretician. I say theoretically it appears that it's got a very, very high speed, and gravity has a very high speed. They're basically the same equations. I mean, you can have a pointing type vector for gravity with these elements in it, the same thing. And therefore, I feel that. So there is some experiment. I have a reference whose reference I've forgotten now because I didn't know you were asked this question. There is an electrostatic experiment that has been done to indicate that perhaps electrostatic fields are established at a very great velocity. But work has to be done, and if you or I made a proposal to the University of Aberystwyth, well, it doesn't have to be Aberystwyth, I just see you there, James, or the University of Dublin or anywhere, the University of Texas, they would say, you're talking through your hat, we won't fund it because all these things cannot exceed the speed of light because that's what the special relativity theory says. But we need to have data. We don't have the data.
Well,
I have a different take on this, but anyway, let Jim go ahead.
Well, the many of the arguments and observations, so-called apparent observations that Ian just cited, in a way, might support the idea that the gravitational phenomena is not based upon mass, as I've argued in previous presentations. So that's a whole nother point of view.
Yeah, I think you might have raised that once when you gave a presentation, and perhaps I asked a contiguous question. And I'm not sure. I mean, there are obviously maybe parallel ways of thinking. Whether they come together or whether they diverge, I don't know. But it's an interesting point anyway.
And the bigger question, after all this is cosmology discussions, what are the implications for what you presented today in cosmology? If, for example, the velocity of some of these effects is far greater than the speed of light, or even say 3 or 4 times the speed of light, what implications does that have in terms of our cosmological models and possible errors in them due to a misunderstanding that these things conduct faster than what we might have thought before?
Yes, indeed. And I frequently conceive of this as explaining what Einstein actually called the spooky action at a distance. And you referred to a moment yourself, Jim. So, that's a contradiction. It's like a Big Bang. It's infinite speed, or it's dividing by zero. So this might resolve that problem. There's no spooky action at a distance, but there is almost instantaneous communications. And it might explain the sort of Machian type ideas, the Machian principle, where anything I do now is determined by the universe, which is billions of light years away and having an effect upon me. Well, it seems far-fetched, but maybe there's something in that because there are interactions between me and maybe, like it doesn't take 4.3 years to get an effect from Alpha Centauri to me. It might take microseconds. It is having some gravitational effect.
Okay, anybody else? All right, I've got a comment in here, and that is if you could share your presentation again. Could you put up the slides again for us?
Now or at the later stage?
Yes, go.
Okay, yeah,
See
okay.
if we can get the slides. Okay, now,
Sure, of course.
my thought on this is you've got a complicated electromagnetic theory, okay, and your electromagnetic theory is, as I see it, this experiment is sort of testing whether the electromagnetic theory is valid or not.
Or
So
it's sufficient. Like
Yes.
it's not
Exactly.
general enough. Yeah.
Right. So the question is, you have those equations. I wanted you to put those equations back up. They're pretty complicated.
You've accepted my request, have you?
Yes.
Okay.
See if we can get back to those. And
Yeah. Okay. Now the only thing is I have to do that again, which I've forgotten how to do. Let's ask Robert again.
Yeah, like
Here I have it. I have it.
I think Harry might be touching on the possibility that this data contradicts electromagnetic theory.
Oh,
Well-
which I I
Yeah,
deferred from because I said I'm not as orthodox with regard to Maxwell as maybe David Toe might be, but I'm near it. I think his ideas were very right, but they're not general enough.
okay, let's go back to slide
Can
2.
you see my slides?
Yes,
Yeah.
Okay. Two. What was two?
that's the second slide.
No, the third one.
Oh,
Fourth
that's
one.
2. Okay, so we
Oh,
need
this
to
is the
go.
one,
Oh,
is it?
here it is here.
There.
Okay,
That.
there it is there. Okay, so we've
Okay.
got all these equations. Now,
Right.
my question is this Maxwell's theory, or is this something more general than Maxwell?
Yeah, that's a very good question. Well,
What I see this is that you're testing the basis of this system of equations, because this system of equations seems to be, we go to the next slide down. Yeah, you've got some
yeah,
equations down here. So what you're doing is you're saying we can test the validity of the theory by whether or not we can actually measure electro-longitudinal waves. So it seems to me this is a test on electromagnetic theory. And as such, then I would think you would be able to sell this to the academics. Okay.
yeah.
You see what I'm driving at?
I think I do. But what I was going to say in answer to your first point is it seems to be basically Maxwellian, but it is an extension because take Poynting's theorem, which follows from Maxwell. This is Poynting's theorem there.
Right.
But he didn't develop that until maybe some decades after Maxwell. Yeah, it
Correct.
doesn't. Yeah, so the same thing here. Yeah, Maxwell does talk about a vector potential, but the problem is the notation, and he talks about a scalar potential, and he has these waves. Yeah, so this all is all Maxwellian, but you know, Maxwell wouldn't have explained it in this term. It did require further work. Where we diverge from him, that's all Maxwellian. That's all Maxwellian. Is the next slide, as you said, uh, because this Maxwell doesn't give equations for that, but Wesley does.
Okay, so my question would be, is this a way of testing electromagnetic theory? Or can they just say, I mean, do these equations actually follow from the theory? It would appear to me the math is good.
Yeah,
So why, if the math is good, and apparently the Texas group isn't challenging the mathematics behind this, they're just questioning the experimental proof. It would seem to me that at some point, you would have a proposal to the academics to say, we need to test electromagnetic theory. If there are or not longitudinal waves, this puts constraints on the correctness of our theory, right?
yes and no. So yes, I mean basically yes, or if you like, testing the completeness of electromagnetic theory. But the slight no there is because I didn't use the word electromagnetic. I say this is electromagnetic, and I said that's electrodynamic. So you could claim that electromagnetic theory is complete and correct, and I've added something to it, which is not part of electromagnetic theory. It, but you could also say it is part, and therefore electromagnetic theory is not complete because it hasn't got this green bit in.
Right.
On
So
the next slide, you show a waveform.
Which one?
The next slide, the one that showed the frequency modulated wave.
oh, it's further up. You passed it.
That?
No, further
No,
up.
I think it was the next one after the one you were showing.
I'm finished now. That's the end.
No, you're
Well,
going
you
in the
have to
wrong
go up.
direction.
Go back.
Back. Go
Go back.
back.
That
We're
that.
talking
Yes.
about that.
Right there. That looks to me like frequency modulation. So that are you defining a longitudinal wave as frequency modulation? Is that your defining criteria?
no, it's not my defining criterion. Uh, I'm. It is true that these things are dependent upon frequency because the distance between the compression where you have a very high frequency is the wavelength, and the difference between when it's stretched out, the rarefaction is the frequency. But no, I'm not talking about frequency modulation at all. I mean, you might ask, can these things be frequency modulated or can they be amplitude modulation? That's a whole other study. Perhaps they can be. I haven't looked into
But
that.
are you saying that a wave that looks like it's frequency modulated, or at least the carrier for a frequency modulated signal, is produced by a continuous frequency signal in the transmitter?
No, I'm not even saying that. I'm not going into that. I'm just saying that, and we've had debates about these things. You know, I've said that um, according to the theory here, and we believe there's some experiment, although people like Franklin Hu would say there's no experiment to show this is right. This is Maxwell's model. He has this in his book. Um, you have well, you have the wave is being carried this way, okay, but at right angles to it, you have an E field like that, and it's modulated if you like, or it's within an envelope, and you have a B field there at right angles to it. So that's a transverse wave. Well, we could talk in terms of mechanical water waves or seismic waves, but keeping to the electrical, this is the electrical magnetic transverse. Now, I haven't, well, I haven't actually shown the E field, but had I done that, I would have had an E field. I would have the wave moving in that direction, and I would have had the pointing vector carrying the power, and I would have had an E field, which you call it modulate if you like, but I would say varies uh, depending upon the way the wave is transmitting. So the E field is very concentrated here, and then it's spread out. So, in other words, the E is moving in, just like the molecules of air would in a sound wave. It would change the density of the local.
Yeah, I don't think a sound wave traveling changes frequency.
Yes, you're absolutely right.
Um,
Let me ask you the question about the medium. Do we need ether or some kind of medium to transfer your longitudinal waves?
yeah, I'll have to think about that frequency point you just made. The answer to that would Vladimir would be yes. I mean, I would say, and I'm extending Wesley's ideas now, but I would say that ether. I'm not afraid to use the word. Is a fundamental part of this because with the electromagnetic, you have these factors here, and they are factors of the ether.
No, mu zero is not. It's a vacuum. It's not ether. Without
Oh
ether,
no,
it's an ideal situation with Maxwell equations too. There is no medium at all. That's why, guys, and we know that there is plasma around Earth, there is a cosmic medium, whatever. But do we have this? We took into account or not? This is the very first question. The second question, guys, I wanna stress the point that all our radio waves, they are not going inside of our wires or balls, whatever. All of them exist in vacuum, I don't know, around these wires, around these, balls. That's why you cannot avoid any transverse waves if you have any wires going to your ball. How to cut it, I don't know. Look, it's very important issue. Electromagnetic waves, they are running around wires. They are not inside. You cannot cut them at all. And the same story with receiver. You have your ball, and then you have your wires to some instrument, to some, test procedure. That's why to avoid this extra transverse radiation, I don't know how to do it. You cannot do your something with your ball only, without these wires around, and they all of them transmit the radio waves, all of them, on the way to your balls.
Okay. Well, you've raised a number of points there. Just before maybe coming to them, yeah, you're right here. I mean, this diagram might have been a bit confusing, but it's just a diagram to show that it could be a sound wave, and the compression is the, the compression of the gas. So you're getting a higher pressure there. And similarly, a rarefaction is a lower pressure. It's not the
Yeah.
frequency changing. Yeah, you're right to point that out.
But then don't show this, sinusoid. It's a pressure changes inside of our vacuum or inside of our medium.
Yeah,
I don't
I think
believe
this
in
was a bit.
vacuum at all.
I
Do you
stole this
have
diagram.
any chance to take
It's a
into
bit of an
account any
illustrative
influence
thing,
of the medium on your equations?
as if it were a spring, and you have the spring which is compressing and letting out. So don't worry too much about it. It was just a model. Yeah, you've raised a lot of points, but I don't know. I don't want to dismiss them. I think they're secondary. You've talked about what happens in the wires and and the medium and the so-called vacuum, the vacuum speed of light, which I've always delineated as C0, is the speed in the ether, the ordinary ether, without any disturbance. Because there's no such thing as a vacuum in my analysis.
The definition is speed of light in vacuum. It's a definition. There is no ether, there is no medium, there is nothing.
According
The
to
same
who?
story with
According to
your
Maxwell, there isn't
longitudinal
any.
waves.
What I've just said is orthodox. Maxwell would totally agree with me. The speed of light in vacuum is equal to the speed of light in the ether.
I don't
It's
understand.
physics which
I'm
disagree
sorry.
with.
All right.
I'm wondering if any of the discussions that have arisen from the stimulating talk from Ian, and thank you, Ian, has some impact on Robert French's work in electricity and charged particles and so forth. Not to put you on the spot, Bob, but
Yeah, no, it's okay. But were you thinking of anything in particular there?
No, just all, a wide range of issues. I'm wondering if you haven't said much today, and I was wondering if any of these issues have an impact on your own work.
Yeah, they might. I've always thought of light as being a transverse wave, but it looks like for Ian, he admits that there are transverse waves, but in addition, he's also talking about these longitudinal waves, and of course, sound waves are longitudinal waves. But one point is like with this spooky action at a distance that Einstein is kind of poking fun at, but which I think it exists. It's not so much as going from a source out to a receiver as what happens when you have two potential receivers which jointly absorb. So as far as I can see, and of course I hold an emission theory, is the speed of light is c from the source out to the receiver. But once you have this joint effect occurring, that just occurs within the time of joint absorption. The best estimates I've seen there is like 10 to the minus 8 seconds. So I notice the whole thing's completely instantaneous, but it's like the joint effect occurs over a great spatial distance. And whereas I think, Ian, that you're saying that something just propagates very quickly, but not like instantaneously. Am I right there?
You are, and I was going to say that because you've just validated what I was going to say, Robert. Because as far as I remember from your presentations, you also do accede to this idea of certain forces like gravity, for example. I think you mentioned that yourself, if I'm not incorrect, as propagating much, much faster than light.
I'm not sure how fast gravity propagates. I actually thought of it as probably propagating at the speed of light, but I really don't know if I have evidence. There's some evidence, for gravitational waves and things, and you don't have to tie that as confirming general relativity. Other theories can also say they're gravitational waves.
And by the way, I make a distinction between gravitational waves and gravitational interaction. So I conceive again from the theory, I conceive of gravitational waves as traveling at the speed of light because they are disturbances in the ether. The ether, any disturbance in the ether is determined to interact at a speed which is 1 over the square root of epsilon naught mu naught. So they're etheric waves. And therefore, some of these experiments they've done about gravitational waves may not be very far off the mark because they're actually disturbances in the ether. But I'm talking about gravitational interaction. Gravitational interaction seems to be another thing. It's like electrostatic interaction. And it seems to be practically instantaneous. Now, I think we're in agreement that they're not instantaneous. I don't like that as a mathematician. That would mean the speed is infinite. But they're very, very rapid.
Yeah.
Vladimir.
Yes, guys, first of all, many times I told you there is no speed of light in vacuum. Maxwell equations, they have C as a ratio of electrodynamic charge to electrostatic charge. So need electrodynamic constant. It's not speed of light. Well, no, in these experiments, we don't speak about light. It's some radio waves. For radio waves, it's well-known effect for fast radio bursts. There is a dispersion of radio waves in our ether or in my cosmic medium and so on and so on. That's why don't name the speed of light and prescribe it to Maxwell. He didn't know anything about speed of light. He knew about electrodynamic constant measured before him, maybe 10 years before, with some other scientists. That's why, don't confuse us with this speed of light. I don't understand this definition at all. We are talking about light right now, or we are talking about radio waves. Where is the
We
light?
blame
Where is
that
the
on
end of the
Einstein.
light? Huh?
We'll blame Einstein for this. I think that's where it comes
But
from.
I don't totally concur with that.
Einstein, it's a geometry. It is something ideal. It doesn't exist in a real life at all. We must forget about Einstein right now, guys. Geometry. We live in physics, not in geometry.
The stress to the strain, effectively, or the stress to the density of the ether, if you can look at it that way. Now, Maxwell was actually looking, in 1873, at the measured speed of light. Going back to Foucault.
No, it was close enough. He compared his velocity based on his equations.
That's right.
And then he compared to experimental results measured by some other guys. And you know what was his conclusion? That light, in your words, light is electrodynamic phenomenon. That's it. He concluded. He never talked about this exactly the speed of light. Never. On the contrary, his conclusion was, it means for me that it's electrodynamic constant. It's because, the electromagnetic waves, light is electromagnetic waves. That's what he told.
We might be arguing about semantics here.
I refer to his own words about it.
Well,
many times in my papers.
For me, it's the speed of transverse electromagnetic radiation. Now, if you want to substitute that phrase for speed of light, I'm not going to start arguing with you. The speed of light is one aspect of that because light, according to the Maxwellian theory, is one form of transverse electromagnetic radiation. But you could argue until you're blue in the face about this. To me, it's not that important. But I do agree that Einstein has probably confused the situation by bringing in this as like almost like something that we always have to concentrate on, the speed of light, speed of light, speed of light. And he actually talked about the velocity of light, which would mean that he's taking in the direction as well.
Well, he makes it into a fundamental constant of physics, whereas I think what Vladimir is pointing out, it's an electrodynamic constant.
That's an agreement with me, I think.
Wrote in his paper,
I agree with that. We don't differ. It's just we express it in a different way. I talk about the speed of light, but it's a shorthand for this electrodynamic constant. And you saw that I did put in, and you may have said, I might have put c squared 1 over c squared in there. I put in epsilon naught mu naught in a lot of these equations. So that's all ever in my mind. I agree.
Epsilon is not, it's our ideal vacuum situation. There is no medium at all. That's why in all your equations, you must put extra members, some parts of your equations based on ether, on cosmic medium, on whatever.
So
On
are you
cosmic plasma.
saying, you see, to me, I think there's a difference between us here. To me, epsilon naught is the value in the ether. Now, epsilon, it could be a value in some other dielectric medium, which would be epsilon naught times epsilon r, the relative permittivity times the absolute value or the value in a vacuum. But you seem to be saying that epsilon naught is a theoretical concept. Correct me if I'm wrong. In a
Yes,
non.
yes, it is for absolute medium, perfect medium, whatever, it is not ether.
Well,
It's
it
not
is
ether
ether in
in
my
his world.
definition. We could argue about this at some other time, but if you're looking at my equations, I just want to make clear, you might disagree with them, but no, epsilon naught is in the ether and mu naught is in the ether. And if you have a medium, which is outside that, you have to put in a relative permittivity.
In your ether, what are the parameters, physical parameters of your ether, except epsilon zero and mu zero? What else? What
There is
kind
one
of
other parameter.
parameters, physical parameters you have of your ether?
There is one other parameter which I put in, and I've talked about this, which is non-existent in the theories of relativity. It's sigma naught, which is the conductivity.
Conductivity means immediately you have some matter. You must have electrons, protons, and all this stuff. What kind of conductivity?
You've been arguing about this on the emails for years, and fine, good luck to you. But I told you that I'm not ready to speculate on that. Whether it's positrons and electrons, whether it's the lattice thing, whether it's nothing, all I know is I know what the properties of the ether are, and I can give you values. I can give you values for those. Sigma naught is not so well known, but epsilon naught and mu naught are. And we can do experiments and we can replicate that. Now, whether the electrons are bound in rings or whether they're doing this or the other, that's another question. And good luck to you. I'd be interested to hear your results, but that's not what I'm concerned with at the moment.
About intergalactic plasma, I told so many times I have no other words. That's why I talk many times about fast radio bursts and dispersion of them. It means immediately you have intergalactic plasma. And they calculated even the density of this intergalactic plasma. It's not me, it's them.
But
And
that's
it's
an additional
exactly
thing.
what I calculated in my theory.
That's an additional thing, and you've talked about that. But what you conceive, and I think maybe Jerry asked you this some time ago, what you conceive and describe as what do you call it, cosmic medium, uh, sounded very much like an ether, and you demurred from using the term ether. And I'm not sure if you answered that very satisfactorily. You seem to object to that, and I don't know why.
Sorry, no. It's some kind of your ether, because in your ether there is no composition of it. I gave you
I don't know
cosmic
what the
medium and
composition is.
difference
I
from
don't think there's
ether
none. I
only.
don't know what it
Then
is.
I saturated this ether with some particles, with some real stuff in this cosmic medium. That's why I gave new name, not ether, because ether, I don't know what does it mean. I am physicist. I want to ask you immediately, what is the composition of it? You gave me some additional parameter, fine, but what is the composition of it? And I gave gas in cosmic medium real composition. These particles, protons, electrons, neutrinos, photons, and universe created particles. I saturated with physical meaning your ether. Yes, it's some kind of ether, but I have some real stuff. Like air around us, we have some stuff, oxygen, nitrogen, and all this stuff. The same story I've done with my cosmic medium. You can see it like an ether. It's fine with me. But your ether means for me nothing, because there is no some existence of some particles or something inside of it. You gave the parameters, but parameters for vacuum, they don't exist. It should be ether. If it's ether, tell me what does it mean, your ether? What is the composition of it? Simple like this. It's exactly what I started over 20 years ago to ask myself these questions about ether and what is the composition of it.
I'd
Well,
be
we have
interested to
lots of
know.
theories about that.
I'd be interested to know more about Ian's sigma naught parameter and how it relates to the permeability and permittivity parameters. Perhaps at some future time, Ian can enlighten us about that work.
Yeah, I'd be happy.
Okay, we've got, let's see, 3.5 minutes, barely.
So, could Ian just summarize a few things we've talked about, the recommendations for the experimentalists, just to summarize, because there's too much theory being talked about.
Yeah.
The whole point of this is to encourage experimentalists to have another go.
Yeah, I'm in two minds about this, James, but I think there's no reason why one should object to proposing that a further repeat of the Monstein-Wesley type experiment be done. I mean, if we're correct, all we have is the original experiment of 2002 and the Butterworth experiment of 2011 or whenever it was. If we did another experiment, and some of the comments which have been made by people here, like Jim started, would be well worth taking into account, and maybe interference from cables such as Vladimir mentioned. So that would be worth doing, and therefore there would be some other minds maybe involved in that if it were an academic project, James, who would be able to give a fresh idea. You see, we're all biased. Monstein and Wesley, I mean, I have a lot of respect for both of them, but they're biased. And I made a bit of fun, maybe, I do confess, about the Butterworth dismissal, that we just don't know what it is, but it cannot be longitudinal. Well, they have biases as well. They're eminent academicians in Texas University there. But I'd love fresh minds to be put upon this, do the experiments, and therefore try to analyze it. I think that'd be well worth a project. And I must say that I didn't demur from Denny's proposal that he and I get an experimenter to do it, and we'll do all the analysis and so on. But we get him to set up all the apparatus. And I mean, if you had connections, we'd be happy to work with you, James, for example. Denny is still on for this.
I don't really, but yeah. All I say is that when I was at university, I did a project with the simplest apparatus possible, a girding condenser, a big capacitor to measure atmospheric conductivity, and I found out something about it's all on the.
I looked it up. You have it on the web. I was impressed with that. Very good work.
Yeah. And I basically found out a new mode of operation. So even the simplest things can get. I mean, for a young physicist, this is very rewarding, perhaps, to try and solve these sort of little conundrums.
And you were probably an undergraduate at that time, were you?
Yes. Yeah.
So, in other words, this project could perhaps be promoted as an undergraduate project, a fourth-year project or something. Where you get the opposition is these big academicians who think they know it all and they don't want to open their minds to new ideas, and they would dismiss it. But maybe that's the avenue to go, to get some students to do the project.
Yeah. The only trouble is it's the wavelength is a meter, so you have to have a big, laboratory to do it in. I don't know what the size of hertz
No, you
is.
could scale it down. You could scale it down a bit.
Yeah.
Okay, we got about 30 seconds left. I want to thank everybody for participating this morning. Thank you, Ian. Good job.
Thank you.
Thank you all.
A lot more conversation and discussion than I was thinking was going to happen.